Welcome back to College Algebra. In this video, we're going to be looking at linear and nonlinear systems of equations. As its name suggests, a system of equations is a collection of several different equations in two variables. And a solution to the system is a point which satisfies each of the equations. So if I have, say, the equation x plus 2y equals 5, and 5x minus 3y equals 7, each of these equations represents a line in the two-dimensional coordinate plane, and the point where those two lines cross each other is the solution to the system. So graphing here in Desmos, I can plot those points, I can find the intersection, and to identify, in this case, it's something in the ballpark of 2.2, 1.4. We can do the same thing with a nonlinear system of equations. If I clear these two equations out of the way, I might look at something like the circle x squared plus y squared equals 16, the circle with radius 4, and I might look at a parabola, y equals x squared minus 1. This system of equations has two solutions. There are two places where the two curves meet each other. In this particular case, they happen to be symmetric. And we can identify those using the graph as well. About 2.1 and 3.4, and then negative 2.1, 3.4 are the 2 points. Of course, it's not necessary that two graphs overlap each other. For example, if I graph the circle x squared plus y squared equals 1, and I graph the line x plus y equals 3, the line very clearly misses the circle entirely. We call a situation like this an inconsistent system. And so we can jump back to the notes sheet, which is right here, and try to solve systems of equations, because while graphical solutions do certainly work, the problem is that they give approximate solutions. And this being math class, we're going to be looking for exact solutions, which means we're going to want to try to find tools to solve algebraically. The substitution method is my method of choice for solving a system of equations when one of the equations is already solved for a particular variable. For example, 2x plus 3y equals 5, y equals 3/4 x minus 4. Because this second equation is solved for y, A simple way of solving the system is to take that second equation and replace the value of y with the expression in the first equation. So we'll have 2x plus 3 times y, which is 3/4 x minus 4, is equal to 5. Distributing 2x plus 9/4 x minus 12 is equal to 5. 2x plus 9/4 x equals 17, getting all the variables alone. We can rewrite 2 as, I guess, 8/4, so we have some common denominator fractions to work with. 8 plus 9 is 17. And then to get x by itself, we divide both sides of the equation by 17/4. All right, I'm running a little bit low on space, so let me scroll down a little bit, but not too much because I still need that equation that we started with. I get that x is equal to 4 in this case, which is good and important, but not the end of the story, because we are talking about coordinates in two-dimensional space. We need an x value and a y value. So now that we have this value for x, we can take it and put it back into one of the equations we started with. And since the thing we are looking for is y, it makes sense to put it back into the equation that already has y by itself. Y equals 3/4 times x, which is 4, minus 4. 3/4 times 4 is 3, and 3 minus 4 is -1. So x equals 4, y equals -1. We will write our solution as the ordered pair for -1. The method of substitution works for solving linear systems. It also works for solving nonlinear systems. So as an example, consider a system involving a circle as well as a line. X squared plus y squared equals 20. Y minus 3x equals -2. This particular system does not have either equation solved for any one variable, but it does have the linear equation as the second component, which can be easily solved. For y, simply add 3x to both sides of that equation, and we get that y is equal to 3x minus 2. Now that we have that, we can plug that in to the value of y in the first equation, and we get that x squared plus y, which is 3x minus 2 squared, is equal to 20. Multiplying that out, 3x times 3x is 9x squared. 3x times minus 2 is minus 6x. We'll get 2 of those, so that's minus 12x. And then minus 2 times minus 2 is plus 4. All right. Combine some like terms. I'll also subtract 20 to get this looking like a quadratic equation. 10x squared minus 12x minus 16 equals 0. I can even divide both sides of the equation by 2 to get some slightly smaller coefficients to work with. although technically speaking, I don't need to do that. 5 times -8 is -40. I can't think offhand of any two numbers that multiply to -40 and add to -6. There probably are some, I just can't think of them. So I'm going to resort to the quadratic formula. X equals the opposite of b, opposite of -6 is +6, plus or minus the square root of b, which is -6 squared, minus 4 times a, which is 5, times c, which is -8, all over 2 times a, which is still 5. See, 6 squared is 36. 4 times 5 is 20. 20 times 8 is 160. 36 plus 160 is 196. And the square root of 196 is 14. Splitting this up into the two possibilities. 6 plus 14 is 20. 6 minus 14 is -8. 20 over 10 is 2. -8 over 10 reduces to -4/5. In a nonlinear system of equations, we get two possible values for x. This might correspond to two possible solutions. It might not. We have to go back to the original equations and see. This particular problem, my original equation scrolled off the screen, so let me scroll back up. And once again, I could take either equation, but I'm going to look for the one that is already solved for y. That's going to make my life a little bit easier. Y equals 3x minus 2. I can plug in x equals 2. Three times 2 is 6. 6 minus 2 is 4. So the point 2, 4 is a solution to this system of equations. I should also plug in the solution x equals -4/5. Y equals 3 times -4/5 minus 2. I'm going to rewrite 2 as 10 over 5 so that things look normal. And -12 minus 10 is -22. So I get that -4/5, -22/5 is also a solution to this equation. And so with that, I have solved a nonlinear system of equations and gotten two possible solutions. Let's take a look at one more linear system before we move onward. How about the linear system 2x minus 3y equals 4, and y equals 2/3 x plus 3. Looks like a perfectly normal system of equations. Once again, I have one of the equations solved for y, so it makes sense that I should use the substitution method and substitute this value of y back into the first equation. So we have 2x minus 3 times y, which is 2/3 x plus 3, and that should be equal to 4. Distributing, 3 times 2/3 is 2, minus 3 times 3 is minus 9. 2x minus 2x cancel each other out with 0 left behind, giving me the result -9 equals 4. We ended up here with no solution. And that is definitely a thing that can happen. We saw in the graphs we were looking at the very beginning of this video that you can sketch out a graph where a circle and a line don't intersect each other. It's also certainly possible to have two lines which never intersect each other. We call that situation parallel lines. And if you check and find the slope of that first line, you will find that it is 2/3, exactly the slope of the second line. Two parallel lines will never cross each other. We say that this situation is one where the system has no solution. We also sometimes call this an inconsistent system. Moving onward, let's take a look at another tool for solving systems of equations. It's called sometimes the addition method, but I prefer the name of the elimination method. And the addition method or elimination method is the most useful when you have two equations which are not straightforward to solve for a variable. For example, if we have a system of linear equations where there are coefficients on all of the variables, solving for a particular variable is not impossible, but a little bit annoying. Consider the system of equations 2x minus 5y equals 3 and 4x plus 3y is equal to 1. I could solve one of these equations for one of the variables. It would work. But that's not the plan of action that I have. Instead, I am going to attempt to eliminate one of the variables. What I notice in this particular system is that the coefficients of x are multiple of each other. 2 times 2 is 4. And so because of that, I can use the multiplicative property of equations and take this first equation, multiply the whole thing by 2. When I do that, I get 4x minus 5 minus 10y equals 6. And I'm going to take that second equation and I'm going to multiply by -1. When I do that, I get minus 4x minus 3y equals -1. adding these two equations together. The addition property of equations says that you can add the same thing to both sides of an equation without changing the equation. An equation itself, our first equation here, says that 4x minus 10y is the same thing as 6. So if I take the second equation and I add 4x minus 10y on the left-hand side and I add 6 on the right-hand side, well, then I've gone through a very complicated way of adding the same thing on both sides of the equation, which is perfectly valid according to the addition property of equality. But I have carefully set this up so that when I do that, 4x and negative 4x, combining like terms, those go away. And we're left without x in the resulting equation. Combining like terms, negative 10y and minus 3y is negative 13y, and 6 minus 1 is 5. This is called the addition method sometimes because it uses the addition property of equations. It's called the elimination method sometimes because we have carried out a process to eliminate x from our equations. Either way you think about it, it's the exact same result. Negative 13y equals 5, which means that y itself is negative 5 over 13. Now we have to solve for x. We can choose either of the equations we started with. There's no real advantage to one or the other in this case. I'm going to go with the first one because it's the first one. So I substitute in the value y is negative 5/13 into that first equation. Multiplying out, that's plus 25 over 13. And while I'm at it, I'm going to rewrite 3, that's 39 over 13. And now we have a common denominator to work with. So I can subtract 25/13 from both sides of the equation to get 14 over 13. And finally get x by itself by dividing by 2. 14 divided by 2 is 7. So I get that the solution to this system of equations is 7 over 13, negative 5 over 13. Let's take a look at one more system of two linear equations like this before we get to the more challenging things. Quite honestly, for systems of two equations in two variables, unless things are set up exactly perfectly, the elimination method is more trouble than it's worth. The substitution method tends to work better. But the elimination method is powerful because it will allow us to solve more complicated situations easily. So we use these cases of simple linear equations in two variables as a warm-up to get used to the elimination method. Let's take a look at 4x plus 7y equals 10, and 5x minus 3y equals negative 11. In this particular system of equations, there's not really any common factors. There's nothing we can use to make the process more straightforward. We're going to have to use a brute force strategy. We can choose to either eliminate x or eliminate y. I notice in this particular system that the coefficients on y have opposite signs, positive in the first equation, negative in the second. That makes things ever so slightly easier to eliminate y, but it really doesn't matter. We just have to choose one and go with it. So I have to ask the question. If I take the first equation and multiply by something and the second equation and multiply by something else, what will get the coefficient on y to have the same magnitude but opposite signs? Well, the obvious approach is the opposite coefficient. The second equation has a coefficient of 3 on y. If I multiply the first equation by 3, that will get that factor of 3 there. The first equation has a coefficient of 7. If I multiply the second equation by 7, that will get that coefficient into the mix as well. All right, 12x plus 21y equals 30. 35x minus 21y is equal to negative 77. Adding these two things together, I get that 47x is equal to negative 47. And dividing, I get that x is negative 1. Now that I have this, I can go back to either of the equations I started with. It really doesn't matter which one, and substitute in that value for x. If one of them looked nice, for example, if I have a fraction as my value of x, and one of the equations has a coefficient that will cancel out with the denominator of that fraction, it's going to be a little bit easier, and I'll choose that one. But in this case, I don't really have anything, so I just default to the first equation because it comes first. But you plug that value in, it turns into a fairly straightforward linear equation in one variable. There's not really anything new we have to learn about that. Solve the equation. You should be able to do that in your sleep at this point. And we get the solution. X is negative 1, y is 2. That's the ordered pair, negative 1, 2. The method of elimination can be very powerful when you have a system of equations that doesn't have an obvious way of substituting. Or even sometimes when there is an obvious way of substituting, it's a little bit challenging to use. For example, if I have the system x squared plus y squared equals 12. This is the circle centered at the origin with a radius of 2 square roots of 3. And then I have the equation this system gives me a circle as well as an ellipse. But more importantly, this system gives me an equation involving x squared and y squared, and another equation involving x squared and y squared. There is no obvious way to solve either equation for x or y. Or there is, but it's going to involve some square roots and some ugliness, and I'd rather avoid that. So this is a situation where I definitely prefer using the method of elimination. Conveniently, the first equation in this system has coefficients of 1 everywhere, so I can just choose whatever I want and set up the elimination fairly straightforward. Let's go ahead and take that first equation and multiply both sides by negative 2. Negative 2x squared minus 2y squared is equal to negative 24. And I'll leave the second equation alone exactly how it is. The minus 2x squared and plus 2x squared cancel each other out. Minus 2y squared plus 5y squared is 3y squared. And 40 minus 24 is 16. All right, so I get that y squared is 16 over 3, and taking the square root of both sides of the equation, well, square root of 16 is 4, square root of 3 is square root of 3. Square root property says this could be positive or negative, and then I'll rationalize to get that y is plus or minus 4 root 3 over 3. Now that I have a value of y, in this case, actually, I have two values of y, the positive branch and the negative branch. I want to take each branch and plug it back into one of the equations we had to start with. The first one has a slightly easier coefficient, so that's the one I'm going to use. X squared plus 4 square root of 3 over 3 squared is equal to 12, which means that x squared plus 16 times 3 over 9 is equal to 12, or x squared plus 16 over 3 equals 12. While I'm at this, I might as well rewrite that 12 using common denominator. 12 is 36 over 3. And when I subtract, that means that x squared is 20 over 3. X is going to be plus or minus the square root of 20 over the square root of 3. 20 is 4 times 5, so that's 2 root 5. And then rationalizing, multiplying top and bottom by root 3, I get that x is plus or minus 2 square root of 15 over 3. So that gives me the two solutions. Positive 4 root, no, sorry, x comes first. Positive 2 root 15 over 3, comma, 4 root 3 over 3, and negative 2 root 15 over 3, comma, 4 root 3 over 3. I'm running out of screen real estate, so I'm not going to go through and plug in the negative value of y, but take that negative branch, negative 4 root 3 over 3, plug it back into the same equation. After the first step, the algebra looks identical, and you get the same x solutions. So that gives you the other two solutions to this system. 2 root 15 over 3, negative 4 root 3 over 3, and negative 2 root 15 over 3, negative 4 root 3 over 3. Right. This system of two nonlinear equations has 4 distinct possible solutions. Cranking this up one step further. So far, we have stuck with equations involving two variables. There's no reason that we needed to. We could just as easily look at a system of equations that involves 3 variables. (2x plus 3y minus z equals 4), 3x minus 2y plus z equals 2, 5x minus y plus 2z equals 6. I know my handwriting can be atrocious at times. My 2's and z's tend to start looking alike. which is why I put the slash through all of the z's so that you can tell them apart from the 2's. To solve a system of 3 equations in 3 variables, we are going to need to do a copious amount of elimination. The first step is to choose a variable and eliminate it, and then eliminate it again. I'm going to be throwing a bunch of equations around. To help keep track of what's going on, I'm going to name the 3 equations that we've started with here as equation A, equation B, and equation C. And I'm going to choose one of the variables to eliminate. In this particular system, it looks like Z is going to be the easiest one to eliminate, because if you notice in those first 2 equations, if I just add them together, Z will be eliminated right away. And that's exactly what I'm going to do. I'm going to take equation A plus equation B. So that's 2x plus 3y minus z equals 4, and that's 3x minus 2y plus z equals 2. When I add these together, 2x plus 3x is 5x, 3y minus 2y is plus y, z's are gone, and 4 plus 2 is 6. This is now an equation that has only 2 variables in it, not 3. And that's incredibly useful. So useful, in fact, that I'm going to immediately name this guy. Let's call that equation D. Before I get to using equation D, I want to do this whole process over again. I looked at equations A and B already. Now I need to bring equation C into the mix as well. I can use either of equation A or B that I've already started with so that I have 2 equations to work with, but I need to also include equation C. And since I eliminated z's in the first system, I must eliminate z's in the second set as well. Right. So I'm looking at definitely using equation C. C has a coefficient of positive 2z. A couple of ways I can do this, but I think the easiest is to take equation A and multiply by 2. Then I'll have a coefficient of negative z. So equation C as it is, 5x minus y plus 2z equals 6. And twice equation A, which is going to be 4x plus 6y minus 2z equals 8. And when I add these 2 equations together, I get 9x plus 5y equals 14. And again, the key here is that I chose 2 equations, A and B, and I added them together. I could have used coefficients if I needed to, multiply each equation by something, so that I eliminate one of the variables. I chose to eliminate z. I could have chosen any of them. Then I grab the third equation, and then I reuse either one of the 2 equations I started with. And I perform elimination to eliminate the same variable I eliminated before. This gives me another very useful equation. I will call it equation E. Now I have equation D, which has just x and y. I have equation E, which has just x and y. My goal here is to solve this system of 2 equations in 2 variables. I could rearrange and use the substitution method at this point, but I'm going strong with elimination, so I'm going to keep doing that. It looks like if I leave equation E alone and multiply equation D by negative 5, good things will happen. So I'm going to take equation E, and I'm going to take minus 5 times equation D. All right. So equation E is 9x plus 5y equals 14. Minus 5 times equation D is minus 25x minus 5y equals negative 30. And when I add these together, 9x minus 25x is negative 16x. 5y minus 5y is 0. 14 minus 30 is negative 16. And divide by negative 16 to get that x is 1. I've now solved for x. Now I have to go back to equations I've already worked with to solve for y and for z. I don't want to go back to one of the original equations just yet because the original equations have too many variables in them, right? They have x and y and z. I need an equation that has just x and y. That's either equation D or equation E. I could, once again, choose any of them. I'm going to choose equation D. So let's scroll down for a moment and rewrite equation D. Which is 5x plus y equals 6. Plug in that x equals 1. We have 5 times 1 plus y equals 6. 5 plus y equals 6, and y equals 1. There's a second value, second variable that we have solved. Now I have both x and y. Now I can go back to one of the equations we started with. So I have to scroll all the way back up and choose one of equation A, B, or C, which are the only places that still have the variable z in them. I can choose any one of them. It looks like equation B is going to be the easiest to work with. 3x minus 2y plus z equals 2. So I'll come down here and I'll rewrite equation B. 3x minus 2y plus z equals 2. And I will substitute in that x is 1. And I will substitute in that y is 1. That will give me 3 times 1 minus 2 times 1 plus z equals 2. That's 3 minus 2 plus z. 3 minus 2 is 1. And subtracting 1 from both sides of the equation here, I get that z is equal to 1. Just like we have ordered pairs x, y for two-dimensional space, we have ordered triplets x, y, z for three-dimensional space. And in this particular problem, I got that x is 1, y is 1, z is 1. So the solution is the ordered triplet 1, 1, 1. All right. So now let's take a look at some problem solving involving systems of equations. Here, we are looking at mixing antifreeze. A chemical company makes two brands of antifreeze. The first brand uses a 60% concentration, and the second brand uses an 85% concentration. And we want to mix these two antifreezes together to create a result that has a 75% concentration. How many gallons of each should we combine to create that mixture with the 75% concentration? There are, as always, several ways to solve a problem like this. The method that I'm going to use is to set up a system of equations. And it can be confusing when you start putting arbitrary variables into things to remember which variable means what when you're done. So very commonly when we set up problems like this, and we've seen it before, I'm going to start by saying let X be the number of gallons of the 60% solution. And then let's let Y be the number of gallons of the 85% solution. And with just those two facts, we can start trying to put some things together. I know that half of the problem is missing. We need not just the concentration, but we also need to know how much stuff we want to get in the end. Our goal is to fill up a 50-gallon drum with this antifreeze mixture. That's important. Without that information, we won't be able to solve the problem. How much of each should we purchase so that when we mix them together, we get 50 gallons and it has a 75% antifreeze concentration? And that is an important statement to know because, first of all, it gives us an equation to work with. If we add together the number of gallons of the 60% solution and the number of gallons of the 85% solution, we should end up with 50. I'm going to label that the total gallons solution or total gallons equation so that I remember why I wrote that down later on. The other thing we want to think about is how much actual antifreeze is in these mixed chemicals. If I take 60% of X that will tell me how many gallons of actual antifreeze are in the solution. The rest of the solution is the solvent, probably water, maybe some sort of alcohol that the antifreeze is dissolved into. Likewise, if I take 85% of Y, that will be the number of gallons of antifreeze that we get out of our 85% solution. The rest of the solution, again, being water or whatever solvent we happen to have used. And then finally, if I take 75% of 50, that's how many gallons of actual antifreeze I need in the solution I end up with. And I've gotten that 75% of 50 actual gallons of antifreeze in my final solution by tracking the number of gallons of actually antifreeze in each of the two solutions we combine together. So I want to take 60% of X, which is 0.6X. I want to take 85% of Y, which is 0.85Y. I want to add them together, and I want to get 75% of 50, which is 0.75 times 50, or 37.5. Right, that's my concentration equation. That's how much actual antifreeze am I getting out of this process. And with that, I have two equations with two unknowns. I can solve this system of equations to get my final solution. And I can use either the substitution method or the elimination method. Either one is perfectly valid. I'm going to rewrite them a little bit closer together. And I'm going to take that first equation and multiply by, say, negative 0.6. Negative 0.6 times 50 is negative 30. And when I add these things together, I get that x's go away. Negative 0.6 plus 0.85 is 0.25y. And negative 30 plus 37.5 is positive 7.5. Dividing here, 7.5 divided by 0.25 is exactly 30. So I get that y is 30. And then plugging that back into the equation that I had to start with, 30, no, x plus 30 equals 50. I get that x is 20. And so with that, I have my solution. We need 20 gallons of solution X, which was the 60% solution. And we need 30 gallons of Y, which was the 85% solution. All right. And with that problem, I am going to wrap up here. Thank you, as always, for joining me, and I'll see you next time.